Hi everyone, today we're going to learn about L'Hopital's rule. L'Hopital's rule is a technique that helps us evaluate certain limits when direct substitution doesn't immediately give us an answer. So you'll see here at the top we have the lesson objectives, and then before we start, I want to go over what you should already know before going into this lesson. You should know how to evaluate limits using direct substitution. You should know your algebraic techniques, and you should also know how to find derivatives of basic functions because L'Hopital's rule uses derivatives. Okay, so let's go ahead and start with our first example. Now, whenever I see a limit, the first thing I do is substitute the value into the original expression. So let's substitute 3. When we substitute 3 here, and again, we're doing that because it's the limit as x approaches 3, we have 3 squared minus 9 over 3 minus 3. 3 squared is 9. 3 minus 3 is 0. 9 minus 9 is 0 over 0. So after substituting, we got 0 over 0. And I'm sure a lot of you would probably want to say it's just 0. And why can't we just say it's 0? The reason is that division by 0 is undefined. We cannot divide by a 0, so 0 over 0 is not a valid answer. Which leads me into what we're going to talk about next, which is indeterminate forms. Now, indeterminate forms means that we do not have enough information to determine the limit yet. So there are two indeterminate forms that allow us to use L'Hopital's rule. And those are 0 over 0 and infinity over infinity. If substitution gives you either of these two forms, we may use L'Hopital's rule. So let's go on to the steps of L'Hopital's rule. And we're going to use that original example up here to follow these steps. So step 1, which we already did, is substitute. So I'm just going to rewrite it for the sake of the example. And we got 0 over 0. So step 2 is actually recognizing that if you get 0 over 0, you use L'Hopital's rule. So because we got, so step 2, I'll write 0 over 0 or infinity over infinity. Use L'Hopital's rule. And step 3 is actually using the rule, which is to differentiate the numerator and the denominator. Okay, so we're going to differentiate numerator. So in our case, we're finding the derivative of x squared minus 9, which is equal to 2x. And then you're going to differentiate the denominator. So take the derivative of x minus 3, which is just 1. So step 4 is to evaluate the new limit, and we're going to use substitution again. So now we have the limit as x approaches 3 of 2x over 1. And then we're going to go ahead and substitute in that 3. 2 times 3 is 6. 6 over 1 is 6. So your final answer is as the limit as x approaches 3 of x squared minus 9 over x minus 3 is equal to 6. Okay, so let's try a few examples together. So this first example is as the limit as x approaches 0 of sine x over x. So we're going to go ahead and substitute the 0 into this original equation. So sine of 0 over 0. The sine of 0 is 0, and the denominator is just 0, so we see that we have an indeterminate form. So we're going to go ahead and move on to step 2. We've recognized that, and now we can differentiate both the top and the bottom. So the derivative of sine is cosine. So I'm going to rewrite this. So the limit as x approaches 0 of cosine x. And then we're going to differentiate the denominator. So the derivative of x is just 1. Now our new limit is as the x approaches 0 of cosine x over 1. And now we can go to that last step, which is just to substitute. So the cosine of 0, and then all over 1. The cosine of 0 is 1. 1 over 1 is 1. So the limit as x approaches 0 of sine x over x is equal to 1. It's not the greatest box. Okay, so now let's look at an example with a different type of limit. So instead of x approaching a number like 0 or 3, x is now approaching infinity. And before we do anything, I just want to remind some people of we're not plugging in infinity because infinity is not a number we can just substitute into the function. Instead, we're asking ourselves what happens as x gets larger and larger. Okay, so let's start with the numerator. If you look at an example, like let's just say x is 2, then the numerator is e squared, which is about 7.39. Now suppose we plug in another number like 5. It's going to come out to e to the 5th, which is about 148. Then if you plug in 10, you're going to get an even bigger number. And every time I keep plugging in a bigger and bigger number, e to the x is getting bigger. So that means e to the x is actually approaching infinity. Now let's look at the denominator. Okay, so we have if x is 2, if we plug in x is 2 here, our answer is going to be 2. If we plug in 10, it's going to be 10. So that means that every time we plug in a bigger number, x itself is also going to be a bigger number, and it's going to keep getting bigger. So that means our denominator is also infinity. So now we see that we have infinity over infinity, which is an indeterminate form. And now we can apply L'Hopital's rule. Okay, so we're going to go ahead and differentiate. So we're going to do the limit as x approaches infinity. Now, the derivative of e to the x is just e to the x, and the derivative of x is 1. Now we're going to do the same thing we just did. Nothing changes because as x approaches infinity, e to the x is also approaching infinity. But now the new denominator, because it's just 1, it's going to stay as 1, and then anything over itself is itself. So the limit as x approaches infinity of e to the x over x is infinity. All right, we're going to do something similar with the next example. So again, the limit as x approaches infinity of 3x squared plus 5 over x squared minus 4. Again, remember, we're not substituting infinity. Instead, we're looking at what happens as x becomes larger and larger. Now, if you use that same type of reasoning that we did in the problem before, if you just substitute in numbers, and if you make those numbers bigger and bigger every time, you'll notice that 3x squared plus 5 is going to keep getting larger. So it's going to be infinity. It's approaching infinity, I should say. And then we're going to do the same thing with the denominator. As x approaches infinity, x squared minus 4 also approaches infinity. Those numbers are going to keep getting larger. So again, we notice that we have an indeterminate form, so we're going to use L'Hopital's rule. Now we're going to take the derivative of the numerator and the denominator. So if we look at the numerator, we have 6x, and then the derivative of the denominator is 2x. Now, if you divide those, 6x over 2x is 3. And we don't even have to do the direct substitution anymore. So the limit as x approaches infinity of 3x squared plus 5 over x squared minus 4 is equal to 3.
Okay, so this is Maddie here, switch of teachers here. So let's move on with this next problem. If we are doing the problem right here, where we are evaluating the limit as x approaches 0 of e to the power of x minus 1 over x, the very first thing we want to do is directly substitute in our value of 0 for x to see if we can even use L'Hopital's rule. So if we plug in 0, we get e to the power of 0 minus 1 over 0. E to the power of 0 gives us 1, and then we have minus 1 over 0, which this simplifies to 0 over 0. Since we have that 0 over 0, we have an indeterminate form, which tells us that we are now able to use L'Hopital's rule to evaluate this limit. When we want to use L'Hopital's rule, we are now going to differentiate the numerator and differentiate the denominator separately. So we're not going to be using the quotient rule. We're just going to individually differentiate each of the numerator and the denominator. So if we first look at our numerator when we differentiate, e to the power of x, the derivative of e to the power of x just stays as e to the power of x. And the derivative of negative 1 is 0, so in the numerator, we are just left with e to the power of x. If we now move on to differentiating the denominator, the derivative of x is 1, so we are just left with 1 in the denominator. Now that we have our differentiated limit, we can directly substitute again to evaluate the limit now. So if we plug in 0 for x, we would get e to the 0 power over 1. E to the 0 we know is 1, so we are left with 1 over 1, which tells us that the limit as x approaches 0 of e to the power of x minus 1 over x equals 1. So again, just to reiterate, because we were able to find that when we directly substituted that we had an indeterminate form, we were then able to use L'Hopital's rule to evaluate. If we move on to this next example, the limit as x approaches 1 of the natural log of x over x minus 1. Again, we wanted to follow the same process. The first thing we want to do is directly substitute our value in for x. So if we directly substitute, we have the natural log of 1 over 1 minus 1. This simplifies to 0 over 0. So again, because we have that indeterminate form of 0 over 0, we now know that we're allowed to use L'Hopital's rule to evaluate this to evaluate this limit. So we can differentiate the numerator and the denominator separately and then use L'Hopital's rule to evaluate. So if we differentiate the numerator and the denominator, the derivative of the natural log of x is 1 over x. And then the derivative of x is 1. The derivative of negative 1 would be 0. So in the denominator, we are just left with 1. Now we can directly substitute in that value of 1 again to actually evaluate the limit. So we would have 1 over 1 over 1, which simplifies to just 1. So that means our limit as x approaches 1 of the natural log of x over x minus 1 equals 1. Because we had that indeterminate form originally, we were then able to use L'Hopital's rule to actually evaluate the limit. If we move on to this example on the right, we're going to follow the same process. We're going to directly substitute and see if we can use L'Hopital's from there. When we directly substitute, we end up with 3 squared plus 1 over 5. 3 squared plus 1 is going to end up equaling 10. So we're left with 10 over 5, which simplifies to 2. Now, because we do not have an indeterminate form of 0 over 0 or infinity over infinity, we are not able to use L'Hopital's rule. Since we cannot use L'Hopital's rule from this point on, we can actually just say that the value of this function, or the value of this limit as x approaches 3 of x to the power of 2 plus 1 over 5 is just 2. It's the value that we just found. So we weren't able to use L'Hopital's because we didn't have an indeterminate form, but we did still find the value of that limit. At this point, this is when I would freeze in class and ask if anybody has questions on any of the problems we just did. If we did not have any questions, I would have you flip it over to the next page. There are 2 problems that I want you to try on your own. So at this point, you can pause the video here, give them a try. Remember, first check to see if we have an indeterminate form by directly substituting. If you have an indeterminate form, then you can go ahead and use L'Hopital's rule by differentiating the numerator, then by separately differentiating the denominator, and then directly substituting it again to figure out what the value of the limit is. Pause the video here and give these 2 problems a try, and then we will go through them together. So for part A, if we directly substitute for our first step, we have the square root of 4 minus 2 over 4 minus 4. The square root of 4 is 2, so 2 minus 2 is 0. And then in our denominator, we have 4 minus 4, which is 0. We have that indeterminate form, so it is a go-ahead for us to use L'Hopital's rule. If we take the derivative of the numerator, we can rewrite our numerator, if necessary, to be x to the power of 1/2 minus 2. So if that helps you visualize what we're doing when we're taking the derivative, or when we're finding the derivative, we know that this is going to end up becoming 1 over 2 times the square root of x, since here we would end up with 1/2 x to the negative 1/2. So that would send our square root of x to the denominator of the fraction. And that square root of negative 2 that we're left with right here, I'm sorry, not the square root, the derivative of the square root, the minus 2 that we are left with right there, is just 0. So in our numerator of our limit, we are just left with 1 over 2 root x. If I take the derivative of the denominator now, x minus 4, we would just be left with 1. So now if I go to directly substitute to actually evaluate the limit, I would be left with 1 over 2 times the square root of 4, which ends up equaling 1/4. So the limit as x approaches 4, the square root of x minus 2 over x minus 4 equals 1/4. We had an indeterminate form after we directly substituted, so we were able to use L'Hopital's rule to evaluate. Then when you did part B, if you directly substituted, you would have had 3 plus 1 over 3 minus 2, which would have given us 4 over 1. So since we did not get that indeterminate form of 0 over 0 or infinity over infinity, we are not able to use L'Hopital's rule there. So we can still say, though, that the value we found of 4 is the value of the limit. So the limit as x approaches 3 of x plus 1 over x minus 2 equals 4. And then I would stop and say, does anybody have any questions at this point? And then we would move on to the summary. I want to give you guys about 30 seconds to try and answer these 3 questions on your own, and then we will go through them together. Before I use L'Hopital's rule, what is the very first thing I should do? First, we should check to see. We should directly substitute to check for an indeterminate form. What two indeterminate forms allow us to use L'Hopital's rule? Hopefully a student would tell me 0 over 0 and infinity over infinity. And then what do we differentiate? We differentiate the numerator and the denominator individually. Okay, and now we have an exit slip for you guys to do before you head out. So please complete that exit slip and have a good rest of your day.